Mm-hmm. Okay. Hi, everyone. Thanks for coming. I hope everyone can hear me on Zoom. Please speak up in the chat if that's not the case. It's a pleasure for me today to welcome Michele Perna to give a seminar at the CAB. Michele is currently a postdoc here working on the formation and evolution of galaxies, and specifically focused on James Webb Space Telescope observations, which is what he's going to talk to today, which is what he's going to tell us today about. So Michele started his career at the University of Roma, where he did his bachelor's and master's degree, and then he moved to Bologna to complete his PhD. After that, he moved to Arcetre. Have I said that correctly? Yeah. And just outside of Florence, where he was a postdoc for 2 years. And in 2019, he won an Attracción de Talento fellowship and brought that here to the CAB. And now he's sort of continuing on his research here at the CAB as a CSIC postdoc. So I'll let you take it away from here, Michele.
Thank you, Lee. So good morning, everyone. I'm Michele Perna. I'm at CAB as a postdoc, working with Santiago Arribas and many other people in the extragalactic group. The work I'm going to present today is obtained as part of the JWST GTO team JADES. JADES is an ambitious program of very deep infrared imaging and spectroscopic observations obtained with different instruments on JWST with the aim of studying very distant galaxies and active galactic nuclei. So this is the outline of my presentation. I will start with a brief introduction about black holes and active galactic nuclei, normally known as AGN. Then I will introduce very briefly the role that these supermassive black holes may have in galaxies, in galaxy evolution. And then I will introduce the discovery of very distant AGN and quasars before the JWST launch, and then the discovery of these of the most distant AGN in GNZ11 at redshift 10·6. In the final part of this presentation, I will discuss our current knowledge about the black hole formation in the evolution, mostly focusing on the different kinds of black hole seeds we may have at very high redshift, and then all the processes of feeding and feedback that drive the evolution of these black hole seeds into the supermassive black holes that we observe at high redshift. So just start with the black holes. We have two different families of black holes in the universe. The stellar mass black holes, they have masses from 2 to tens of solar masses, and they are generated at the end of the massive stars' life cycles. Here is a collection of supermassive stellar mass black holes. In purple are the ones observed with electromagnetic radiation, while in blue you see the ones observed with LIGO-Virgo gravitational waves. Then there is another family of supermassive black holes. They have, well, another family of black holes are the supermassive black holes. They have masses higher than 10⁴ solar masses, and probably the most famous one is our own Sagittarius A star at the center of the Milky Way. Here is a very nice picture of the supermassive black hole obtained with EHT with the JWST telescope. Now, if we look at the infrared emission in the surrounding of Sagittarius A star, we can identify very bright stars, but at the position, exact location of Sagittarius A star, there is no significant emission. This is because the luminosity of our own supermassive black hole is very similar to the one of the sun. It's because the Sagittarius A star supermassive black hole is not really accreting, and we call this kind of systems quiescent supermassive black holes. On the other side, there are the the supermassive black holes that are very bright. They can be as luminous as galaxies with luminosities higher than 10 to the 11, and they are identified as AGN. Here there is just an example, very nice example, showing a very bright emission from the nucleus, and where you see that the host galaxy is mostly undetected, is associated with this faint envelope. AGN are also among the most luminous objects in the sky at every wavelength. Here there is the spectral energy distribution, so the flux density as a function of the frequency for a standard AGN in black, but also in orange for two different families of AGN. This is for radio loud, and this is for radio quiet AGN. This spectral energy distribution of AGN is shown in comparison with this one, with this curve. This is for the starburst, for a starburst galaxy. And you see that from this comparison that AGN can be much brighter than a starburst galaxy at several wavelength regimes. In this image here, what I want to show you is the very first quasar ever discovered. This is very famous, 3C, sorry. This is 3C273 at redshift 0.2. As I said, this is the very first quasar ever discovered in 1963. And it was the first time that astronomers associated very bright sources in the radio with point-like sources, so star-like sources in the optical. From here is the name quasi-stellar radio sources. This one instead is one of the latest and more distant AGN, supermassive black hole, ever discovered. This was discovered a few months ago. It is at redshift about 10, and it was discovered combined JWST observation with very deep Chandra observations. We can also use optical surveys to study AGN. In particular, optical spectra can be used to distinguish between type 2 AGN and type 1 AGN. In particular, the type 2 AGN here in the top is associated with a stellar continuum you see here with some transition in absorption due to the stars, in addition to very bright narrow emission lines associated with both forbidden and permitted transitions. The full width at alt maximum of these transitions is 500 kilometers per second. And these spectra also show a wide range of ionization stages. So for instance, we can have this transition with a ionization potential of 10 electron volt, but also this one, the helium-2, that has more than 50 electron volts. Then there are the type 1 AGN. The main difference with respect to type 2 AGN is the presence of a very bright continuum, power law like continuum. Then, of course, we also have the emission from the narrow transition. But in addition to them, we also have these very broad profiles associated with permitted emission lines. So in particular with the Balmer lines. And in this case, the full width at alt maximum can be of the order of a few thousand kilometers per second. Of course, there are many other families of AGN. I'm not going to introduce all of them, also because all these families can be in some way combined in a unified scheme. This is a well-known unified model that is used to explain all the differences, in particular between type 1 and type 2 quasars and AGN. It is also very nice because here all the elements in this picture can be associated with some emission we saw in the spectral energy distribution and in the optical spectra of these quasars. In particular, there is the accretion disk here in the middle that is responsible for the continuum power law I showed you before. Then we have the narrow line region clouds that are here in the external part. This can extend out to kiloparsec scales, are due to the interstellar gas that is ionized by the AGN radiation. and is responsible of the narrow emission lines I show you in the previous spectrum. And they have electron densities of the order of 10 to the 2 or 10 to the 10 to the 3 particles per cubic centimeter. Then we have the broadline region clouds that are here in this image. They are broader just because are very close to the supermassive black hole, and so they are under the direct influence and gravitational influence of the black hole. They can also have electron densities much higher than 10 to the 8 electron per cubic centimeter. The last element is the dusty torus, this torus here, that absorbs all the photons that are emitted from the central region, so the accretion disk and the broadline region, and re-emits this radiation in the infrared. Now, according to this unified model, the differences between type 1 and type 2 can be just explained considering a different orientation of the observer with respect to the axis of this torus. So, for instance, we may have an observer with this line of sight. For this observer, it will be possible just to look at these components, so at the narrow line region, and this observer will classify this target as a type 2 AGN. But for another observer with a line of sight very close to the axis of the torus, it will be possible to observe narrow line region, broad line region, and also the accretion disk. So this observer will classify this target as a type 1 AGN. Of course, this is a very simplified scheme. Reality is much more complex than this, and many other parameters could be required in more sophisticated unified models. But this sketch is very useful for this presentation, and this is also supported by some observations. So for instance, here what I'm showing is the very innermost regions of this galaxy, of this AGN, that shows this conical structure that are associated with the narrow line region. And there are also other observations that pointing to the presence of this torus obscuring material very close to the central supermassive black hole. For the role of these supermassive black holes in galaxy evolution, we have to consider that some connection between supermassive black holes and galaxy evolution started in late 1990s after the publication of a series of papers showing some correlations between the properties of the supermassive black hole, and in particular, the black hole mass that is reported here in this axis, and other properties of the host galaxies. Here in particular, I'm showing the mass of the bulge of the galaxy, and you see that there is this very nice correlation. There were also other similarities. Here in particular, what I'm showing is the star formation history as a function of the redshift in black, in comparison with the black hole accretion we have as a function of the redshift in green, in red, and also in blue, using different tracers. And you see that they have essentially the same shape across the cosmic epochs. So in order to establish this connection between supermassive black hole and galaxy, of course, we need a supermassive black hole that communicates its presence, so from subparsec scales to the host galaxies up to kiloparsec scales. This can be done considering that the energy released by a typical supermassive black hole during its life cycle is about 100 times higher than the binding energy of the host galaxy. This means that if we consider that just a fraction of this energy can couple with the ISM in the host, then we can have significant effects just due to the presence of this radiation from the AGN. So for instance, we can have some heating in the host galaxy, or even some ejection of material from the host galaxy. This is, for instance, this is another cartoon showing from Ciccone et al. Showing the generation of some winds from the accretion disk of the supermassive black hole that couples with the ISM and then generates very strong outflows that in principle are capable to remove the material from the host galaxy, and so to stop the formation stars, and also the accretion on the supermassive black hole. Of course, this is a cartoon, but again, we have some observational confirmation for this scheme. Here, for instance, is shown the ejection of material up to scales of 1 kiloparsec from the center of this galaxy. And in this case, even we have, again, ejection of material with very high velocities of the order of 1,000 kilometers per second from the central region of this key galaxy. Even stronger effects can be observed in radio galaxies. Here, for instance, we have very powerful jets that can expel a significant amount of gas and material up to scales of hundreds of kiloparsecs from the central black hole. So let's move to the next part about the discovery of AGN and quasars at high redshift before the launch of JWST. So this is a cumulative function distribution of all the discovered quasars at redshift higher than 5 as a function of the year of the publication. Of course, you see a significant increase in the number of discovered quasars in the last years. This is, of course, because of the increased sensitivity and capabilities of our instruments. And this is even without considering all the very recent results we obtained with JWST. What I want to point out, however, is that if we move all these sources in a plot like this, showing the luminosity of the AGN as a function of the mass of the black hole, well, we see that all the newly discovered AGN and quasars, here reported in red, are very extreme in comparison with all the other AGN at lower redshift that are reported here in blue. So this means that they are very massive and they are very luminous. Here in this other plot, I'm essentially reporting the same information. In this case, is again the AGN luminosity versus the redshift. These are all the quasars observed before the JWST launch. With JWST, we started to discover many other AGN and quasars that are less luminous than the one previously discovered. The problem with these, with all these quasars, in particular at very high redshift, is that they are very massive. Here I'm showing again the correlation I reported at the beginning of the presentation with the black hole mass versus the mass of the galaxy. And this one here in dark green is the correlation we observe in the local universe. And you see that all these newly discovered quasars at high redshift are significantly above this relation. This means that these quasars are as massive as some of the largest quasars we have in the local universe, and they had just a few hundred mega years to accrete such material. So this is a problem. But for now, let's move to the discovery and the characterization of GNZ11 at redshift 10.6. So this is the most detailed picture we had for this system until a few years ago. This was obtained with HST observations. This galaxy was initially selected as a Lyman-Breck galaxy candidate at redshift higher than 10. This technique, the Lyman-Breck selection technique, works on the arguments that all the radiation that is with an energy higher than the Lyman limit, so that is at 912 angstrom, is essentially suppressed, is essentially absorbed by neutral material that is surrounding the star-forming regions. So in real data, what we would observe is, with respect to the reference of the star, is some emission above this wavelength, so 900 angstrom, and no emission at lower shorter wavelength. So we have a dropout or a break in the spectral energy distribution of these galaxies. This is essentially what was observed with HST. So you see here the photometric measurements from HST, and this drop here, and then essentially no detection at shorter wavelengths. In 2016, OH and collaborators also published this very low signal-to-noise spectrum that essentially was pointing to the presence again of this break due to the Lyme absorption. Of course, they provided this tentative redshift 11.09, but you see the spectrum, the quality of the spectrum was very low. This is instead what we got with JWST. You see that we have a very nice drop here in the continuum. We also have a very signal-to-noise detection of the continuum across all the wavelength range, and we also have many emission lines. So we published this paper for the first time in Bunker et al., and we reported in this paper the final definitive measurement of the redshift for this galaxy. This is not the end. This paper was just publishing the low spectral resolution data, but then we published also these other data. These are obtained in high resolution, or well, in medium resolution with NISPEC. You see that now the emission lines are more well defined, and we detect many emission lines from Lyman alpha up to H gamma. All these emission lines are detected at very high signal to noise. These emission lines allowed us to derive many results. Among them, we could study for the first time the ISM properties in this very distant galaxy. So for instance, the ionization, the metallicity, and also the star formation in this system. And this was also the first object at redshift higher than 10 for which we could confirm the presence of Lyman alpha emission. So what I'm doing in this slide is just to compare the properties of GNZ11 with one of the Milky Way. We can see from this slide that a Milky Way galaxy in the local universe is more massive than GNZ11 of a factor of 1,000. Milky Way galaxy is also more extended. The size is more than 25 times larger than GNZ11. If you want, GNZ11 is in this red box here. But the star formation rate in GNZ11 is much higher. We are talking about 30 solar masses per year in comparison of 1 solar masses per year here, when the universe was just 400 million years after the Big Bang. So the main similarities between these two galaxies, and in particular between GNZ11 and Milky Way, is that both have a supermassive black hole with a similar mass of the order of 1 million or a few million solar masses. So the identification of the AGN in this system was reported in this paper published on Nature, led by Roberto Maiolino, and providing several evidence for the presence of an AGN. In particular, some emission lines that are unambiguously associated with AGN radiation, and also some evidence for the presence of very strong AGN winds. But let's go in order. So this is the emission line with the highest ionization potential in the spectrum of GNZ11, and you see it is detected at 2 sigma confidence level, and well, this can be interpreted as an ambiguous tracer of the AGN. We also used the line ratio between the nitrogen at 1483 and nitrogen 1486, because you see that it can be considered as a nice tracer of the electron density in GNZ11. So what we have is essentially the detection of just one line. So on the basis of the this argument, we could constrain the electron density for GNZ11, and we found that electron densities higher than 10 to the 7 or 10 to the 8 are required to explain our data. This is telling us that there is a broadline region in this target. The only problem is that the full width at half maximum of this line is of the order of 500 kilometers per second. And I say at the beginning that broadline region should have much broader emission lines of the order of thousands of kilometers per second. But this one can actually be explained considering that black hole mass is proportional to the square of the full width at half maximum. And if we consider that the black hole mass of the GNZ11 is 10 to the 6, this is totally compatible with a full width at half maximum of this order of magnitude. We also detected these very nice peculiar profiles in the carbon-4 emission lines. These are called p-signaling profiles and are indicative of the presence of very strong outflows. This outflow is sketched in this cartoon. Again, we have at the center an AGN, which is launching an outflow. We have the observer here. So the observer will observe an approaching part of the outflow that is blue shifted and is absorbing the radiation and is responsible of this absorption. But we'll observe also the receding part of the outflow here that is responsible of the reshifted emission that we see here. Now, the fact that we observe such very high velocities in absorption can be only explained by the presence of very strong AGN winds. And now I'm going to move in the very last part of this presentation. This is and I'm going to present all the models that have been proposed to explain the formation and the evolution of black holes at very high redshift. So let's start with this picture. This was presented for the first time in Volentieri et al. All these, here there are 3 different channels to generate black holes. All these channels are essentially obtained under the assumption that galaxies at very high redshift are very different from the ones we observe in the local universe. So essentially they are smaller, of course, they are also dominated by dark matter and gas, so essentially with no stars. So let's go through the first channel. The first channel is essentially the simpler one because it considers some physics that are already used in the local universe to explain the formation of stellar mass black holes. Of course, we need to consider that at high redshift, the conditions are very different. So we have a cooling that is very slow. The star formation efficiency is very low at high redshift. So we may consider that just one star forms in a single galaxy at high redshift. This star is very different to the one we observe in the local universe. It's a so-called POP3 star. It has no metals. It can be very massive, of the order of 200 solar masses. And importantly, it can collapse and generate a black hole with a mass of 10 or 100 solar masses per year. Now, the main problem with this scenario of formation of black hole seeds is that these masses are not so high, and then and also that these POP3 stars are generated in random positions within the galaxy. So they have not so many opportunities to grow in mass because of the dynamics of the gas. So other scenarios have been proposed to overcome these difficulties. One of them is the global dynamical instability. So in this case, we may have some global instabilities. So for instance, we may have a structure that is not able to sustain the rotation of the gas in the galaxy. This will originate some strong inflows of gas towards the central parts of the region of the system, and this will generate a very, very peculiar system that at the end will collapse very rapidly into a black hole. These are called direct collapse black holes, and they can have masses of the order of 10 to the 4, 10 to the 6 solar masses. The main problem with this channel of generation of black holes is that they require very specific and rare physical conditions. In simulations, just a tiny fraction of galaxies, simulated galaxies, can originate such heavy black hole seeds. Then we have the last scenario for the formation of black hole seeds. In this case, we don't have global instabilities, we just have local dynamical instabilities. This can generate some gas flows. These gas flows allow the increase in the density in the very central region. Then we will have the formation of the very first stars in a very compact region. This first star will evolve. We will have some generation of first black holes. We will have many collisions among these stars, and possibly the generation of very massive galaxies that at the end will collapse and generate another heavy black hole seed that has masses in this range, 10 to the 3 to 10 to the 4. Again, the problem with this other channel is that they are quite rare in simulations. So now we have these black hole seeds. Of course, we need to follow them in their evolution through feeding and feedback to the formation of supermassive black holes starting from these black hole seeds. So just to recap, we have 3 different channels for the formation of these black hole seeds. We have the ones originating from POP3 stars that at the end provide relatively small black holes of the order with masses of the order of 10, 100 solar masses. The ones generated from the direct collapse that can reach masses of the order of 10 to the 4, 10 to the 6, and then the last ones that can generate from star clusters and obtain black holes with masses of the order of 10 to the 3, 10 to the 4. Now, according to the black hole theories, black hole formation and evolution theories, these black holes, these black hole seeds can form after around 200 million years from the Big Bang. So this means they have just a few 100 million years to grow and go from masses of 10 or up to 10 to the 6 solar masses to 10 to the 9 or 10 to the 10 solar masses, which are the ones that we observe in the distant universe. So to achieve such repeat growth, we need very efficient accretion, very efficient growth. And what we are currently doing is to assume that the accretion on the supermassive black hole is Eddington limited. In this condition, we have that the radiation pressure due to the black hole does not overcome the gravity. So in other words, if we go above this limit, so we can consider super Eddington in some way luminosities, then the radiation pressure will be much higher than the gravity, and the black hole will just push away the material and will stop accreting further gas. So what we can do is to assume that the black hole growth works at Eddington limit. We can start with the observations of the most distant and most massive galaxies and supermassive black holes at redshift about 7 to 8, and then follow the black hole growth track, assuming that they are accreting at the Eddington limit. So if we do so, and we assume that the first supermassive the first black hole seeds can be obtained around 200 million years after the Big Bang, then we can have some baby black holes in this position. So according to this scheme, we can consider that probably the most the favorite scenario would be for a generation of black holes with the direct collapse. This figure is essentially saying the same thing, but here there are many other supermassive black holes. This is from a more recent compilation. But essentially what these tracks are saying is that we have some problems with models for the formation and growth of these supermassive black holes, because here we are assuming that the accretion is at the Eddington limit for several hundred of million years. And this might be not so common. So what happens with the GNZ11? Well, we can do the same exercise. We can start from this, that is the measurement of the black hole mass of the order of 10 to the 6 solar masses at redshift about 11. And then we can assume an Eddington accretion and go back to the very early stages of the universe. And again, we can assume that black hole seeds happen around 200 million years after the Big Bang. And we can consider that, well, probably the most likely scenario for the formation of black hole seeds for GNZ11 is from direct collapse black hole or even from star clusters. There is another important result here. If you want, we can extrapolate this black hole growth up to a lower redshift, and we can see that this black hole in GNZ11 can be the progenitor of the supermassive black holes we see at up to redshift 8. And we can even relax a little bit the criteria, so consider an accretion that is well below the Eddington limit and explain all the other ones that are here below. Of course, we can also consider other scenario. We can consider the possibility of a black hole seed from a stellar remnant, so let's say to 100 solar masses per year, that a super Eddington accretion can go up to 10 to the 6 solar masses in just 100 million years or so. So what we need to do is to understand if the assumptions we are doing are reliable or not, if there could be actually in the universe are continuous gas supply around these early supermassive black holes, and if we should expect that AGN feedback in some way stops the accretion onto the supermassive black hole. So we cannot go above the Eddington limit, because otherwise the accretion will just stop. So what we can do is to use zoom-in simulations to follow the formation and evolution of these early black holes. So this is a video by Michele and shows essentially the distribution of dark matter at the beginning of the universe. After the Big Bang, we have the generation of the first structures. Here the gas is in red. Formation of first structure, first stars is in blue and in purple. And you can see also some white dots that represent supermassive black hole seeds, let's say. And here we have many mergers, the formation of new stars, and at the end, the generation of a disk-like galaxy in 13 giga-years. It is important to note that here there are many mergers, but with the gas, with the stars, but black holes at the end are more or less following this track, but they need more time to go to the final to the central region and accrete to the central supermassive black hole. I think I can go on and show you another video. This is the same simulation, but in this one, there is another piece of information. Now there are blue and red colors for the temperature of the gas. In particular, red colors are for highest temperature. And I think that this is more informative because it also shows the effects of the feedback. So you have at a certain point the explosion of the first stars and also the AGN winds that are responsible of this, well, probably you cannot see very well, but are responsible of this ejection of material and energy outside of the galaxies. Okay, so let's go back to this plot. In this plot now, I'm showing also the predictions we obtained from these cosmological simulations. As you can see, all these curves here are very well consistent with the observations. In particular, these models can be grouped into two different families. We have one family that starts with the heavily seeds and then accretes with super Eddington ratios, for instance, this one in orange. And then we have the other one that start with intermediate or light black hole seeds and go up to the black hole masses of the GNZ11, or also these quasars, going from through periods of super Eddington accretion. You see here, for instance, and then you see the stop in the formation of in the growth of the supermassive black hole just because of the AGN feedback. So what's next? Of course, we still need to work and refine this observation, these simulations. We still need to understand which are all the details about the feeding and feedback in this kind of targets. For instance, we need to understand if from the observations there is actually enough material that can be accreted on the supermassive black hole. So what we did in these two papers, Takel et al. And Scholz et al., was to look for companions around GNZ11, and we actually found different companions, both from imaging and from spectroscopic observations. We also used an ISPEC-IFS data to characterize the close environment of GNZ11. In particular, we found some signature of POP3 stars in this clump that is very close to GNZ11. GNZ11 is here at this position. We also discovered and characterized the Lyman alpha halo around GNZ11. And this halo is very similar to the quasars we have at redshift about 6. And we also identify some evidence for the presence of a narrow layer region associated with carbon-3 gas for GNZ11. There are other upcoming JWST observations and results. So for instance, there is a program by Luis Colina with 20 hours of integration time to study the optical emission lines in GNZ11. We asked for further 50 hours to go deeper in the UV regime and again for GNZ11, but there are also other programs. So for instance, within our collaboration, we have a large program with more than 100 hours to observe 25 AGN at redshift higher than 5. Again, to try to follow the evolution of these systems at a redshift, to try to understand which are all the feeding and all the feedback effects that might affect the evolution of these black holes. So for the conclusion, we discovered a large number of supermassive black holes that are already there, a few million, 100 million years after the Big Bang. I show you the discovery of the most distant supermassive black hole in the universe, in GNZ11. It was just 400 million years after the Big Bang. And I show you that current cosmological simulations can actually reproduce our observations, but they may require some EV black hole seeds and probably very efficient accretion across the evolution of these systems to explain our observations. So we need to discover many more AGN in the very distant universe. We need to better inform these simulations, in particular for these processes of feeding and feedback. And the last point I want to make is that the information about the initial seeding of these early black holes can be washed out during the evolution of these systems. I show you in the simulation that we may have mergers, we may have formation of new stars, we may have supernova explosions, AGN winds. All of them can erase the information about the initial black holes. So we really need to study supermassive black holes and black holes very close to the epoch when they form in the universe. And this is all. Thank you very much for your attention.
Well, thank you very much, Michele. That was a fascinating talk, and we can we've got my microphone wasn't working. So with that was a fascinating talk, Michele. Thank you very much. We can take questions in the room here now, and later we'll have an opportunity to take questions on Zoom. So if there's any questions in the room, please feel free to raise your hand. Miriam?
I'm taking a lot of notes, so I will probably ask you many things at some other stage. But the first one that comes to my mind, in one of the last slides, you said that you guys found evidence for POP3 stars in the helium-2 clump of one galaxy. I don't recall if it was GNZ11. So what were the evidences?
Okay. Yes.
Yeah, here.
Sorry, it was too fast here. But essentially what we found here was a clump. I don't have the pointer. This clump that is very close to GNZ11. GNZ11 is this position. And at this other position, we detect just helium-2 emission. So we know that POP3 stars generate or form in very low metallicity environments. We do not expect to observe any other emission line. And the fact is that in this region, we actually see just helium-2. In this other part, there is also Lyman alpha. There are other transitions in the part below. I show you. Yes. In these other regions, there are other elements. But at the position of this clump, we just see the helium-2. And this might be interpreted as a tentative evidence for the presence of possible presence of POP3 stars. We ask for more deep.
Please let me know what you find. Yeah, my second question was going to be, how do you know it's not another AGN? But you just said that it's because you don't find the other emission lines you would expect.
Yes. In the paper, there is a diagnostic to exclude this possibility.
Okay.
Actually, well, the possible scenario was that the AGN in GNZ11 was capable of explaining the emission, the helium-2 emission at that position. But to do so, we need a much brighter AGN at the position of GNZ11.
Okay.
But again, this is still very tentative because the detection here is probably at 2-3 sigma. And
Paco had a question.
Well, I think Paco wanted to ask how far away is this potential detection from GNZ11?
So I think a few kiloparsec. It should be 0.5, 6, maybe 3 kiloparsec, something like that. A few kiloparsec.
That's pretty impressive stuff. Any more questions here in the room?
We have a question on Zoom. So from Andres, if Andres, you can open your mic and ask your question. Andrea.
Very nice talk. And what already from the IC, they're asking two questions that I also had in mind, but I'm gonna go with mine. What is your feeling about superediton accretion in these very early moments of the life of the black hole? So to accrete so fast, do you think that some models of superediton accretion with photon trapping can help, maybe not completely solve the issue, but can help in explaining those large masses at such early times?
Difficult question. I don't know. The problem is that the Eddington limit can be derived under specific assumptions. So we don't know if these specific assumptions are still valid or in general in the universe, but also at very high redshift. So, well, in principle, I like the fact that, in particular, in this simulation here, I show you with, I don't have it, sorry. So the red solid curve here, the fact that we have a super Eddington phase and then a stop in the accretion is in some way what I would expect. Then I don't know. I don't know if we can really follow at the moment with simulations all the processes that are happening very close to the supermassive black hole. But yeah, in principle, it could happen. Probably, I would exclude a scenario like this one, but I don't know. I don't know.
Thanks.
So we have 3 questions from a team, and they are called YAC Omega. I hope I'm speaking correctly. So the first questions are, first, how was the black hole mass estimated? And also, black holes can grow by mergers. Have you considered this in the analysis?
Okay, so as for the black hole mass measurement, I don't remember exactly which emission line was considered for the estimate of the black hole mass, but I have to say that even at redshift, at much lower redshifts, the uncertainties on the black hole mass estimates can be of the order of 2 or 3 or 4. So yeah, we cannot, we have to consider that there are significant uncertainties on the estimates of the mass of these black holes. I don't think the uncertainties are higher than 1 order of magnitude, but well, we can, I don't know. I will consider the possibility that the uncertainties are of a factor of a few. I didn't discuss about the other very distant quasar observed very recently, the one I mentioned in the introduction. Well, it's also here, I think. Sorry, too many things. Well, never mind. But yeah, so the other very high redshift quasar, the one discovered at redshift 10.1, is here. The black hole mass was derived without any emission line, so just assuming that it was accreting at the Eddington ratio, starting from the luminosity in the X-ray. And they are presenting a mass going from 10 to the 7 to 10 to the 8. So I think that it's true that we have this very massive black holes in the early universe. Then maybe the problem is that we cannot detect the smaller ones. And I forgot the second question, sorry.
Okay, so we have a third and final question. and from the same team, and it goes, do we have an idea of how rare direct collapse black holes are compared to how rare this observed black hole is in terms of mass and redshift?
Yes, I think so. I'm not really familiar with all the literature for black hole seeds. I think that in this very old paper, Voluntary et al. 2012, they say that direct collapse black holes can be obtained just in a galaxy out of 1,000 or 10,000 among the simulated ones. I don't know if more recent simulations provide different numbers. But yeah, I would say that that's not a real problem if we can also rely on other possible channels. So, for instance, the star cluster channel can provide masses up to 10 to the 4. So
Yeah. Okay. So there are no more questions here on Zoom.
Okay. Any further questions in the room?
Oh, and the team says thanks.
thank you.
Well, in which case, I think let's thank Michele again for a fantastic talk. And
Thank you.